Guys, so for today, we're going to continue where we left off, and to make sure that everyone's on the same page, I just emailed you the file that we worked on last time. So if you can either use the one that you made last time or the one I just emailed you. I guess it's safest to use the one I just emailed you. Just because if there's like something in there that we didn't do identically, at least if we're all on the same page with one file, then that should make it a little easier for us to follow along. So there's two files. So one is an MPH file called basic, and the other is some experimental data. So today we'll figure out how to, when we make our plots, we'll figure out how to enter experimental data along with the simulated data. And so remember, when you're comparing simulation data with some analytical model or something else done a different way, that's called verification. And when you're comparing your simulation data with an experimental data, that's called validation. So verification and validation are two different kind of things. Oh yeah, and before we do that, I want to make a little note about what happened last time. So, so John pointed out something to me yesterday that I was kind of interested in, and it had to do with our last assignment. And remember, we were trying to figure out, like, why was the, wait, where says that? Let me open this up. Oh, you're right here. So why was the, this intensity plot asymmetric about the edge here? And if you recall what we had here, we went in here, oh yeah, we entered a 1D group, right? We went in here and did a line plot, and then we selected this line right here, and then we plotted that, and then we saw that as asymmetric, right? See that? So these two should like be the right height, the same height. These two should be about the same height, and that should be, well, that's going to be the center. And we're trying to figure out, like, why was that? And I initially thought it was because maybe the mesh was asymmetric, and it may be a little bit, but it wouldn't cause this great of a change. And so what John pointed out was when we created our geometry right here, he realized that when we created our first, I think this is the first rectangle, it's based on this corner point right here and not the center of it, right? So if you look at our original rectangle, you see here that it's based on the corner, and here's the position, and it went down negative d over 2. So let me draw that in the board over here. So here's the semicircle. And let's say this is cutting it right in half. And when we initially make this, it's born right here, right? And then if we have that go down just d over 2, that means this point right here is going to go down by d over 2 to this position right here. And what we should have done, we should have centered it from, let's say, the center point right here, so that it's like, I'll just draw another one right here. We should have started from this position right here, and then sent that down by d over 2 instead. Because if we do it like this, and then we make a copy of it that's up by some amount d, then the two rectangles are not going to be symmetric about this center dividing line right there. And so it looks like it is center, but it's really not. And so, for example, let's say we change that. Let's say we put in here minus, what did you recommend? I think it was like width divided by 2 or something like that.
Oh, well, in the copy, I just saw displaced it in extra distance.
Oh, you just did it with coffee.
But here you might be able to do it with over 2.
Yeah. So we could have made the change here where we either initially fixed the first one, or what he just suggested, we could have fixed the copy. So let's see if we can do it with the first one. So if we did that, and then we did build all, hopefully you'll see something change here. It's going to change just very slightly when I click on the build all. Yeah, do you see that change? It happened? Just like it went down just a little bit. Now it's centered. So let's see what happens if we were to do our study again. Do that. Let's see what we go down here. Yeah, see? Now it's symmetric. Remember what it looked like before? That's pretty symmetric. Yeah, and in fact, I cannot tell like any difference between the two sides. But that's what we should have got. And so slight little variation does make a big difference. Okay, so I just want to mention that just in case you guys were wondering why it wasn't a better result than it should have been. Okay, and also I think all around it should be symmetric too. So let's go back to the original and let's click on the other sides too to see what we get. Yeah, the whole thing is symmetric too, but all the sides. Yeah, okay, cool. All right. Okay, so that's that. So let's start off by loading up our, I sent you guys this one. It's called Biased Resonator 3D Basic. And so load that up. And so this is where we left off last time. Okay, I can close this. I can go to home, take off Add Steady. Yeah. Okay, so we're going to do a couple of things. And this is just basically doing some analysis here. So the first thing we're going to do, we're going to sweep frequency and look at their frequency response. Okay, so let me remind you of how damping works with these type of things. Okay, so remember this right here is like a basic model of our cantilever. And so if we were going to model that dynamically, we would have mass times acceleration plus the damping times the velocity plus the stiffness times the displacement equal to some externally applied force. And so basically, this is like Newton's law, where here's mass times acceleration, and here's all the forces acting on it. You have some externally applied force, you have some restorative force, and you have some damping force. You can put those on the side, where you can have the sum of your forces. Okay. Now, here's the critical issue right here is damping. It's easy to figure out what mass is, because we know the material properties, we know the geometry. And also, it's very easy to figure out what the stiffness is because of the same reason. Damping, that's another issue altogether. Okay, so for damping, if we assume that there's like Rayleigh damping, where damping is a linear combination of the mass and the stiffness, then we have these two terms right here we're worried about. Okay, and this is actually quite common. And so, oh yes, so for those of you with an ECE background, this equation right here is no different than this equation right here, where you have inductance and acceleration of charge, and you have the resistance times the current, and 1 over capacitance times the charge amount equal to the voltage that's being applied. Both are second order differential equations, constant coefficients, have the same form. The solutions are going to be the same too. Okay. Now we also have a damping ratio that is just a ratio of the this damping divided by the critical damping. And this critical damping right here is usually given like this, 4 times mass stiffness. And for electronics, that would be inductance divided by capacitance. Okay. This is also equal to this right here, 1/2 times alpha over omega plus beta times omega, where the frequency is equal to 2 pi times, well that's angular frequency, 2 pi times the this frequency in hertz. That's in radians per second. So let me also throw this here too, another relationship, where this is about equal to 2 over Q, where Q is the quality factor, okay, and this right here, I'm saying about equal because if you have a very high quality factor, then that relationship holds. And so when we look at our frequency response, it looks something like this, where here's frequency, here's the amplitude on this axis right here, and it'll look something like this, right? And this right here is the resonant frequency. Here's the maximum value. So you would put that right here as like A max. For the quality factor, that's typically somewhere around here. And this value right here that you're looking at is typically A max divided by square root of 2. And you just look at the width of that right here. And then people call that the bandwidth from here to here. Okay, so you can say Q is equal to the resonant frequency over the bandwidth. Okay, and typically the reason that this is under square root of 2 is because a lot of times people are looking at just your raw signal, but then you want to look at it in terms of power. And when you're looking at it in terms of power, you want to know what is the bandwidth at half the power, or it's usually like the cutoff. It's usually half the power. So the way power laws go is that it goes by taking the amplitude, and the amplitude could be anything. It could be displacement, it could be velocity or something, but you're going to square that. And once you square that, then you get your divided by 2 here. Okay, instead of divided by square root 2. Okay, so what's going to say about this? Okay, yeah, so we're going to go into ComSol. We're going to input these two values of alpha and beta. Those are going to be given to us. And typically, these things can be determined experimentally. There are other ways to get this. For example, if you understand, or you knew the viscosity of the fluid or gas, it's flowing. It's flowing through. If it's laminar flow, there are ways to get that too experimentally, but we're just going to enter that in instead of doing it by simulation. Okay, so that's one thing. And this, let me tell you, since we're on this topic, we're also going to look at various modes too. So remember, this whole thing is mirrored. So it looks like this, and we're going to bias this by applying a voltage between these two guys, right? So once you bias this, what happens is that if there's no voltage there, there's no force, and it just sits there at zero state. And then you go perturb it with a small sinusoid to get it vibrating about that point, the operating point. You can bias it by applying some voltage. What that will do, that will dip it down a little bit, and then you perturb it with a sinusoidal excitation about that point. You're going to get different results, and the reason why is because of this. Let's use this as an example. If I don't bias it, and there's no voltage applied between here and here, this is the original point. And if I just perturb it with a sinusoidal excitation, it'll just oscillate like this. Nice sinusoid, right? But if I deflect it down a little bit first with a DC bias, and then I add my sinusoid, and let's say it starts down here, since it's close to this surface right here, what will happen is, as it goes down, it'll stay down here, it'll hang down there a little longer before it goes back up, right? And the reason why is because it's closer to this, which has greater attraction. And so what happens by doing that, it's not like a simple sinusoid any longer, but it is still periodic. And you can see here that the period is actually longer, so the frequency is going to change. And we'll see that, where we will plot on this axis like our voltage. On this axis, we'll plot our resonant frequency, and we'll see that as you increase the voltage, the resonant frequency goes down, which is to be expected as it gets closer and closer. So in that case, we'll look at eigenvectors, look at eigenvalues, and to remind you what those are like. Okay, let's go back to this equation right here. So here's our basic equation, and we're looking at eigenmodes and eigenfrequencies. You typically pretend it's operating in vacuum, so you remove this term right here, and you're just working with this term. Right? And so you can rewrite it like this. And remember, I said that it's a sinusoidal excitation. So you can assume that your x has the form like this. Right? It has some kind of form like this. So we could plug that in here. If we plug that in there too, your x double dot, you differentiate this twice. Along the way, you're going to end with a negative and omega squared, and then the rest. So that part and that part's the same. So you plug those in there, and you get something that looks like this. Okay, and yeah, that negative is going to cancel out now, and also the a is going to cancel out on both sides. So this part, we could rewrite it like this. I'm trying to get this in the form of an eigenvalue equation. Well, do it the right way. These are typically matrices. So let me write it like that. Okay, so this guy right here, that's your eigen value, right? Or you can call it eigen frequency. Okay, and basically it's the square root of that. And these guys right here, these are your eigen vectors. And this is a very common equation in like linear algebra. They're always, well not always, but they solve this equation a lot. Okay, it's this kind of form, and it typically looks like this. Where these are vectors, that's a scalar. Here's like a square matrix. Okay, and so when people say eigenvectors, eigenvalues, you'll know that they're talking about the frequency in terms of like this, or even for circuits, they're talking about the frequency. And eigenvectors, this is where you get the mode shapes. Okay, so this is actually a long vector, and in this simple model, it's a simple one-dimensional structure. But in something like this, you have many degrees of freedom. And remember, we meshed it, and you have like many nodes, you know, with these meshes. And each node has an x coordinate, y coordinate, and z coordinate. So this is a really, really long vector where each node has x, y, and z, and you're solving the shape of that's required to satisfy this equation. And that's why when you look at mode 1, it has one shape. Look at mode 2, it has a different shape. Mode 3, and so on. That's the equation to solve. Okay, so let's get busy with those things. So on this right here, let's do the frequency response first. Oops. Okay, so we loaded up this right here. So let's go to our definitions. I mean our parameters, and let's key in a few parameters. So in the parameter section, let's key in our quality factor, and that's going to be 8,000. Let's key in our resonant frequency, and we're just guessing at our resonant frequency here. So F0, that's going to be 8 megahertz. So it's capital M, capital HZ. For alpha, that's that alpha that I mentioned over here. That's going to be 4 times pi times F0 divided by 3 times Q, the quality factor. Okay, and that's like 4,100 hertz. For beta, that's going to be 1 divided by the quantity 6 times pi times F0 times Q. And that's going to be 8.2 e negative 13, and that's the units of seconds. Can you guys in the back see those numbers? Do I need to repeat that? You guys are good? Okay. Say beta again. Beta is 1 divided by 6 times pi times F0 times Q. I know that Q can look like a 0 here, but that's a Q. And the Q up here, that's 8,000, that Q right there. Okay, so let's now go down to solid mechanics. So we have to open up the component, go down to solid mechanics down here, and then let's go to linear elastic material. That's this first one. Okay, and then let's go down to let's open this up. Oh, we have to add our damping. I'm sorry. Yeah, so right click on linear elastic material and add damping. Here's where we're going to add our alpha and beta. Okay, so here's alpha. It's originally defaults to 0, but we're going to just type in what alpha is. And we defined it as a parameter. Same with beta. Just type in beta. Okay. Next, let's go down to electrostatics. Let's go down to terminal 2. And for terminal 2, let's look at let's go to harmonic perturbation. Okay, and then for harmonic perturbation, right here, it defaults to 1 volt, but let's put it at 0.1. Okay, and remember, like I was saying, what we're going to do here is we're going to put a oh wow. Is that close to here? South College. I know this South College up here.
It's by the library, the intersection of the library and college.
Okay. Okay, well.
Everyone's phone's gonna start ringing.
I already have a yeah, I already have a message already. So it says avoid area, so I think we're okay where we are.
Yeah, we are.
But we'll just see what what else happens if we need to get out of here or something. All right. But thanks. Okay, so so that's our perturbation. So it's going to be a sinusoid, and for example, that capital A right there. Well, for our sinusoid that we're going to apply here, is going to be have a maximum amplitude of the voltage of 0.1 volts, and it's going to sweep different frequencies at that amplitude. Okay. Okay, so now we've done that. So now let's go to add steady. So you can go to up here, and if you click on add steady, it'll just open this up over here, right? And we typically do with add materials, right? But you can add a different steady by doing that. So the steady that we're going to add is going to be, so we're going to go to, let me move this over a little bit. So preset interfaces, we're going to go down to solid mechanics, and then open that up. We're going to go to frequency domain pre-stressed. That's this right here. And once you highlight that, then click add steady. And then I'll add a steady 2 over here. Okay, and so under add steady 2, go to the frequency domain, and the frequency unit, this should be megahertz. So it defaults to hertz, but click it down and click on megahertz. And also for the range, click on this range here. Oh, see, it's calling in right now, AU alert. So click on the range, and for that, for the first one, we're going to start at 7.69. Our step is going to be 0.001, and we're going to stop at 7.73. Okay, so that's going to be our sweep. Okay, so next we're going to highlight, wait, I forgot this, add that, and so it's there. Okay, so now we highlight study 2 again, and then we can relabel this as the frequency domain. And so in this particular study that we're calling frequency domain, that's where we're going to sweep our frequency at that particular 0.1 volt amplitude. Okay, now let's also see where it says generate default plots. Unclick that. That's going to give us extra things that we're not going to look at. Okay, so just unclick that and then click on compute. And that's going to take a few minutes. Maybe like 2 or 3, it looks like. Oh, I should have closed this right here, this add study. Yeah, so when this gets done, I'll click on this again right here to toggle that off. So while we're waiting for that, we should get something that looks like this right here, if we did it right. Almost done. Now remember, we were doing it with the step size was 0.001, so lots of steps between the start and the end. Okay, so it finished calculating. Are you guys all done too? Almost? Okay. So the next thing we're going to do is we're going to plot, tell it what to plot, like what point we're interested in seeing the results at. Okay, so let me know when you're done with this. You guys are done? All right, cool. All right, so let's go to results now. So right-click on results, and then you want to do a 1D plot group. So click on that to create a 1D plot group. So there's, again, in COMSOL, let me close this right here. In COMSOL, there's lots of data, lots of parameters in there, and so you have to tell it exactly what you're interested in plotting. Okay. So for the data set, choose our solution that we just made, which was this is called the frequency domain solution 2. So click on that. So it's going to pull data from there. And then go to right click on this, and then select a point graph. Okay, and we have all these points here. Let me do a transparent right here. So click on that so you can see through it. We're not interested in all these points. We're interested in one. The instructions say choose point 254. So one way to do that is this. You can go to paste section. You click on that. You can type in a point that is already known in hindsight, 254, but you'll see it too. And then click OK. And so, do you see it is blue here, like as if we clicked on that? If you click on this right here, it says zoom to section, our selection. You can zoom in and you can see which one is blue. It's this one right here. So we can unclick it or click it back there. We could click another one if you want to, but that's the one that was chosen. Okay, then we could do zoom extents. Okay, so so after that, let's go down to the expression right here. So the expression we want to plot is not solid displacement. We actually want to plot the z direction. So in COMSOL, it has x, y, and z for the coordinates, but it has u, v, and w for displacement for this. So we're going to put absolute value of w. Okay? And so w is the z displacement in this direction. Okay, and then so now I'll click on plot right here, and then you can see what we got. So this axis right here is absolute W, that's in the microns, and here's the frequency suite from 7.69 to 7.73. And remember, it's 0.001 steps along the way, and yeah. So that's the frequency response of this structure, and okay. So look at the amplitude; it's like 0.6 microns here. But let's say you guys did another coordinate. Let's say you did coordinate v instead of w, and you decided to plot that. It looks very similar, but look at the amplitude, right? 0.004 microns. That's 4 nanometers, right?
And so what you're really looking at in the v direction is along this y axis right here. So this is going up and down, but there's also some type of displacement along the y. It's very small in the range of nanometers. Okay. Let's say we did u. This is going to be in the x direction. If we plotted that, you know, it's not registering anything in the x direction as we oscillate along z, of course. Change it back to w. Okay, so that's that first part. Now let's move on to the second part, where we're going to look at the biased modes, right? So we're going to apply some voltage here, and we're going to look at how the modes change, or how that the frequency of mode 1, how that changes as we apply more and more bias. Okay, so let's try this. How about saving this? Because we're going to start over by just loading up the bias. So save it as something else. So save as, say, basic underscore, I don't know, unbiased frequency or something like that. I don't know. Yeah. I'll put it in square brackets just to know that it's something I modified. Save that. Okay. Now let's go up to open. Let's load up our basic again from scratch. Okay, that's where we started off last time. Now we're going to try to get a plot like this. But also what we're going to do is we're also going to put on here our experimental data. It's going to show up as little, you know, blocks. And hopefully the simulation will match experiment. Okay, so first let's go to our geometry. So here's our geometry here. Right click on geometry, go to transform down here, and let's do a mirror. So click on mirror. Okay, and we want to mirror this whole thing, because so remember, we've only put in this geometry, half of it, but it's really supposed to look like this. So click on here and go Control A, and the two blocks go in there, the two pieces, this one and this one. Okay, and then let's go down here and tell it where we want that mirrored reflection. And we want it, remember, you define it by the normal vector. So instead of having XYZ being 0, 0, 1, have XYZ be 1, 0, 0. Okay, so basically my index finger is the X, and so here's the normal to that. It's like this is the normal to your mirrored plane you're worried about. So X, Y, Z is what your is the plane you're going to do mirror about. And keep your input objects. That's this first part. You want to keep that. Okay? And then do build all. If you do build all, it should look like that. You zoom out, it should look something like this. So that's the complete structure. But it's totally symmetric, so that's why we didn't really have to worry about it when we first made it. So let's go to our definitions next. And then let's go to we want to go into functions, and then click on interpolation. Okay. And then let's go down to our data source, and say it's going to come from a file. So I sent you two things, right? I sent you the MPH file, and oh yeah, the MPH stands for multiphysics. If you guys have figured that out yet. Okay, so I sent you the MPH file. I also sent you a text file, and that text file has the experimental data. So you want to do browse, and you want to click on this right here, experiment. Open that up. It's going to put it right here. Then you want to say import, and once you import it, then it populates that table with that data. Now this first column is a listing of the voltages. The second column are the frequencies. And remember, all this came from experiment. Okay. So what we want to do here is so let's go down to the arguments right here. For this, let's type in the field hertz for this. And for the function, let's type in volts. Okay? And for me, that's kind of weird because when I'm looking at an argument, I'm automatically think, okay, the argument is t and the function is f. But this right here is going to be on the x-axis with volts, and this right here is going to be on the y-axis with frequency, just like we have it here. So it seems to me that someone in ComSol got these backwards, these labels, because it doesn't even match up here, because that's truly a function and the argument is t. But it's a labeling typo. It doesn't change anything in the problem. Now for another thing we have to do is oh wait, we have to go somewhere else too. Oh, okay, yeah. So for here, in this interpolation and extraction section, let's go to extrapolation and then put specific value. And so we have to tell ComSol what to do, how to handle any values that are outside this range. Because remember, it's going to do this interpolation, right? And so anything outside that range, instead of saying 0, we're just going to say not a number. And not a number is capital N, lowercase a, capital N, as usual. Okay. The next thing we're going to do is go to solid mechanics. So we can we'll scroll down here, go to solid mechanics. Let's go into symmetry here, and this is symmetry 1, and it says to choose disable here. Right click on, or maybe we can just do it this way. Yeah. Okay, here we go. Yeah, so right click on symmetry 1. Yeah, I thought it would be in here somewhere, and maybe it is, but I didn't see it right away. But if you right click on it, you can just do disable right here. So you're going to disable that part. Now let's go to the mesh. Okay, open up the mesh and go to size. And for the size, click on custom, and then make the minimum element size, which is right here, the 1.4, just turn that into 1. So the minimum element size is going to be 1. And then say build all. And that should mesh our whole thing. Yeah, there we go. Yeah? What was that? input for the mirror?
100.
Oh, you mean for that vector? Okay. Well, let me go back up to this. Yeah, it was 1, 0, 0 for x. X was 1, and y and z were 0, 0. So let's go back up to right here. Yeah, there we go. So here, so it should look like this, where your normal vector, your plane of reflection is x equal 1, y equals 0, z equals 0. And that's just telling it that's the plane that you're going to do the mirror about. Wait, let me see that. What you got? Oh, wow, wait a minute. This is not even in 3D. How'd that happen?
I just added it to the plane geometry.
Oh, not plane geometry. You add it to that geometry.
Oh, okay.
Yeah. You have to delete that. That should have been more clear. Click on that. Oops. Forms, and then go to mirror. There you go. See, and do a 1, 0, 0. And go. Click on there. Go Control A. Oh wait, it didn't do everything. Try to go Control A. How come? Oh wait a minute, something's wrong here. There's supposed to be other pieces in here. Yeah. I wonder what happened. Let me send you what I have right here. Something happened, but I can't figure out what it is. But I'll save this and email it to you right now. So let's do I'll save it as, I don't know. This is going to be the modal analysis. Let's call it that. And then go here. Yeah, so this is an intermediate kind of step. Okay. Yeah, so that's where we're currently at right now. And yeah, I can't figure out like why your geometry didn't have this extra piece, all these extra pieces in there. That's kind of weird. But yeah, just open it up to this part right here. And then let me know. So you got it? Okay. Yeah, so this mesh here, just telling it what the minimum element size is, and it's going to be 1 micron. And so, yeah, again, the more you guys use COMSOL and get results, you'll get the hang of how to tweak your mesh to get better results that are that converge a little better. That one brute force way of doing that, or weighting, is like I think I told you guys this before, that there's like typically a convergence knee in COMSOL where this direction is like the number of elements right? The number of elements going in this direction. And so let's say there's one element going to, I don't know, 10,000 elements, right? And here's your relative error, right? And so what you find is that your relative error is really high at first, and then it starts going like this, and then there's this little knee where if you get more and more elements, it doesn't really buy you that much anymore. So the question is where is that? And I don't know. But but like, for example, if you're doing your mesh and you get one result, and then you say, okay, well, I'm going to mesh a little finer, and you get like a different result, you'll see where this what happens. Your relative error changes a lot, and then you keep meshing finer and finer, and eventually you'll see, oh, I'm not getting that. My fourth decimal place changes, right? So you passed up that convergence, neat part. So. Okay, so so in this part right here, the size, we put it at 1, the 1 micron for the smallest. So next, let's do it, add study. So let's go to home again. Let's go to add study. And this time, we're going to do preset studies for selected multiphysics. That's right here. And we're going to choose eigenfrequency, this right here. And then click on the plus sign, add study to that. And so now we have our study 2 that's listed here. And so for the step 1 for eigenfrequency, let's click here our desired number. Let's change this to 3 instead of 6. Okay, we're not, we're only interested in the first ones. And what else do we have to change in here? Yeah, that was it. Okay, so now let's go to study. Huh?
Do you want megahertz?
Oh yeah. Well, it doesn't say that we need to change that. If you guys want to change the megahertz, that'll be fine. It shouldn't really, it'll just change the unit, but it's not telling me that we need to change that. Yeah. So I guess. Okay, so let's go to study 2 here. Right click on that, and then go to show default solver, which is right here. Click on that. Wait a minute, why? In the study toolbar, click on default solver. This is weird. I took a wrong turn somewhere. Let me see something here. Okay, I think I got it. So let me back up a little bit so we can get it on the same page. So let me get rid of that first. Okay, so again, we go to in the study toolbar, we click on Show Default Solver. Why am I having difficulty with this? Show Default Solver. We did that. Okay, so that's solution 2. And then from that, we should be able to open that up. Oh yeah, here it goes. And dependent variables. I'm sorry, did I confuse anybody? Okay, so so once you click, okay, so if you're in study 2, and let's go to study here, you click on default solver right here, and then that should open up this, and you should get something called solution 2. Then if you expand solution 2, you should get dependent variables. Okay? And then we go to the general area right here, and then we want to say user defined for this. And then we want to do a couple of things here. So so it's his here on solver configurations. We did that. We go to dependent variables 1. We should open this up, and then we should click on potential right here. And then for potential, what we want to do is, yeah, okay, so I think I know what's happening. There are certain things that it does not want to do, okay? Like when we do this analysis, we want to look at the modes, and we want to not solve for the field and output, okay? And also the same with the spatial mesh. So go to the spatial mesh and do the same thing there. Unclick, solve for the field, and store it in output. Okay, and then what you want to do is go to study 2, and let's just label this as the unbiased eigenfrequency. Okay, and then we want to clear the generate default plots right here, and then once you do that, just click compute. Okay, and now we want to look at the results, but now it's 1:45. Great. Okay, so yeah, there's only like a couple more sections we have to go. Okay, so what we'll do here, let's save this where we're at. Okay, and then we'll pick up on Tuesday to finish this part. But basically, we're getting really close to this. We uploaded our data, our experimental data. Now we're just trying to show how to plot them both together in the results section. Okay, so let's do a save as. I'll just save it like that. Yeah, okay. And also, so on Tuesday when we come back, for anybody who got, kind of messed up along the way, I'll send this email out too. to you guys so we can all start on the same page on Tuesday. All right. So that's it for today. See you guys next week.